So, last time we proved that OK is discrete in R to the n, and we wanted a notion of co-volume of OK in R to the n. Now, I did not want to get into measure theory, so we just defined discriminant. This is supposed to be co-volume of OK in R to the n, and discriminant is a very important invariant of a number field. So, let me recall again what the definition of discriminant is, and we will prove its properties today. Okay. So, let K be a number field of degree n, then we know that OK is a free Z module of rank n. So, let alpha 1 up to alpha n be a Z basis of OK. This is also called integral basis of OK, and we put M to be sigma I alpha j. This is a n by n matrix, right. So, sigma 1 up to sigma n, these are embeddings of K into C. Okay. So, these are embeddings, field embeddings, and discriminant dk was defined to be determinant of M squared, which is same as determinant of M transpose M, and as an exercise I told you to show that this is determinant of trace from K to Q of alpha I alpha j. Okay. Here is another exercise about discriminant. Show that, so this proves the fact that dk is determinant of trace of alpha I alpha j. This shows that discriminant is actually in Z, right. So, it could be a positive integer, it could be a negative integer, it can't be 0 because M is invertible. So, so show that dk is not 0. Okay. So, that is an easy exercise, but another one is show that sine of dk is minus 1 to the power R2. So, remember R2 is the number of pairs of complex embeddings of K, and this exercise is asking you to show that the sign of it is minus 1 to the R2. So, if R2 is odd, then dk is negative, if R2 is even, then dk is positive. Okay. All right. So, now there is no reason for us to restrict to integral basis to define this sort of invariant. We can do it more generally, and it is actually quite useful. So, let beta 1 up to beta n be any q basis of K, and we can define. So, this is of course not called discriminant, but it is defined similarly, delta squared of beta 1 up to beta n to be determinant of sigma I beta j squared, which is of course similar to the exercise above. This is determinant of trace from Q K to Q of beta I beta j. Okay. So, this is again in general a rational number, right. So, if you did all the exercises that I gave you before, you would be able to prove all these things easily. All right. So, why is this useful? Well, one of the reasons why it is useful is because of the following lemma. So, let beta 1 up to beta n be elements of OK. So, they are algebraic integers, and beta 1 up to beta n be a q basis of K. So, they are, So, you are taking a Q basis of k consisting of algebraic integers beta 1 up to beta n. So, if I take the Z span of beta 1 up to beta n is a subring of OK, right. What I mean is that Z beta 1 plus Z beta 2 and so on up to Z beta n, this is contained in OK, right. It is a subring. Okay, so subring in a, well, let me just say subgroup, because ring you may require one to be there, is a subgroup. So, it is an additive subgroup of OK, all right. And so, what does the lemma say? The lemma says, so let M be the index of this additive subgroup. So, let me call this lambda. Then lemma says that delta squared of beta 1 up to beta n, which is an integer now, is m squared times dk. Okay, so, this is a lemma. So, there are two things we need to prove. We need to prove that this m is finite. So, lambda has finite index in OK, and then this relation between delta squared m and dk. But this is just a piece of linear algebra over Z. So, I am going to go over this quickly. So, what you do is you let alpha 1 up to alpha n be a Z basis of OK, right. Then consider the inclusion map Z beta 1 and so on up to Z beta n. This is contained in Z alpha 1, so on up to Z alpha n. But what you can do is you can write each of this so what you can do is, so there exists a matrix A in Mn of Z such that sigma I of beta j is equal to sigma I of alpha j times A, and because this index is because these are linearly independent over, because both beta i's and alpha i's are linearly independent over Q, this map will have finite co-kernel, okay, and determinant of A will be equal to the number of elements in co-kernel of this map I, right, which is equal to M, which is same as OK lambda, okay, all right. And now if you just look at, this is my so delta squared of beta 1 up to beta n, this is equal to determinant of sigma I beta j squared, which is equal to determinant of sigma I alpha j squared determinant of A squared, which is m squared times dk, right. So, we have proven this relation. Okay. One thing I forgot to tell you is maybe another exercise that I wanted to give is that dk is independent of the choice of integral basis of OK. So, this is an exercise that if you do, this proof will become transparent. Okay. So, you should really do this exercise in this is an exercise in linear algebra over Z. Okay. It is nothing complicated, and since algebra is a prerequisite for this course, I can leave this as an exercise. Alright. So, this lemma, which looks kind of harmless including the proof, is actually quite useful when you want to compute integral basis. So, here is a corollary. Let beta 1 up to beta n be in OK such that beta 1 up to beta n spans k over q if delta squared of beta 1 up to beta n is square free, then beta 1 up to beta n is a z basis or integral basis of OK. All right. So, if you know, if you compute this for some q basis of k and it turns out to be a square free integer, then then this beta 1 is also an integral basis of OK. But remember that these beta i's have to be in OK first. You cannot just do it for elements of k that are not necessarily in OK. So, this corollary is easy because m here can only be 1 in that case. Okay. So, this corollary is easy. So, let me give you an example. This is our first example of computing integral basis. So, let k over q be a quadratic extension, and from your Galois theory you should know that any quadratic extension is obtained by adjoining a square root of element, right. So, hence k is equal to q square root of d for some d. We may assume that d is a square free integer, right. Any quadratic extension of q is obtained by adjoining square root of a rational number, but we can clear out the denominators and we can assume that it is a square root of a integer, and of course we can take away whatever squares there are dividing this d, and so we can assume that it is a square free integer. Right. This is a useful assumption. All right. So, in this we know that 1 and square root of d, these are both in OK, right, because 1 is an integer. So, it is also an algebraic integer, and this is a root of x squared minus d. So, it is a monic polynomial over z, right. So, 1 and the square root of d, these are algebraic integers. Now, I compute delta squared of 1 and square root of d. So, what is this? This is determinant of trace of 1 into square root of d, sorry 1 into 1 trace. So, these are all trace from k to q, 1 into square root of d, trace from k to q of square root of d times 1, trace from k to q of square root of d times square root of d. Okay. So, what is this? This is determinant of trace of 1, and trace of 1 is 2, trace of square root of d is 0, trace of square root of t is again 0, and trace of square root of d square, which is just trace of d, this is 2d, right, and so the determinant is 4 times d, right. Now, we know that d is square free, but 4 is divisible by 2 square, right, 4 is 2 square. So, the corollary does not automatically give us that 1 and square root of d is an integral basis, and of course, it is not an integral basis in general, but from this we know the following. We know that hence if lambda equals z times 1 plus z times square root of d, then the index of lambda in OK, this is either 1 or 2, right. And so we want to find out when it is 1 and when it is 2. This means if the index is 2, possibly 2, then this means that z plus z square root of d, this is contained inside OK, and this thing is contained in half z plus half z square root of d. So, this side will never be a, so the second inclusion will never be an equality, but the first inclusion can be strict as well. Okay. So, what we do is we take a by 2 plus b by 2 square root of d in half z plus half z square root of d. Right. This just means that a is an integer, b is an integer. Okay. Of course, a and b could be even, and then a by 2 and b by 2 will also be integer. So, let me take this to be alpha. So, what is the monic polynomial of alpha? So, you take alpha minus a by 2 square, this is b square by 2 times b square by 4 times d, right. So, this is alpha square minus a alpha plus a square minus d b square by 4 equals 0, right. So, you take f of x to be x squared minus ax plus a squared minus db squared by 4. This is a priori a polynomial in Qx. So, this is a monic polynomial with root alpha, right. And so, if this so alpha is in OK if and only if f of x is in zx. This is one of the things that we proved earlier. Now, so f of x is in zx if and only if a squared minus db squared by 4 is in z, right, which is if and only if a squared minus db squared is congruent to 0 mod 4, right. And this happens. So, what does this mean? This means that this is if and only if a squared is congruent to d times b squared mod 4, right. And I know that d is not 0 mod 4 because d is square free. Okay. So, what are the possibilities for d? So, d is congruent to so it is not congruent to 0 mod 4. So, it is 1 mod 4, 2 mod 4 or 3 mod 4, right. So, or 3 mod 4 as d is square free. Square free d is not congruent to 0 mod 4. Okay. Now, I also know that yeah. So, right. So, I can also assume that b is not 0 mod 4, right, because if b is 0 mod 4 then a has to be even as well, right. So, yeah, in any case I want to understand what this is, and so this thing has solution for any a and b, right. So, okay, anyway, so let me continue. So, if b is congruent to 0 mod 2, then A is congruent to 0 mod 2, right, because yeah, I mean, okay, let me write it like this. So, then A squared is congruent to 0 mod 4, and hence A is congruent to 0 mod 2, right. But if B, and in this case of course A by 2 plus B by 2 square root of D, this belongs to Z plus Z square root of D. So, there is nothing interesting happening here, but if B is congruent to 1 mod 2, so it is odd, then B squared is also congruent to 1 mod 4, and A squared is congruent to D mod 4, right. And the only way D is congruent to a square mod 4 is if D is congruent to 1 mod 4. In this case, A is also congruent to 1 mod 4, and hence A is congruent to 1 mod 2, sorry, A squared is congruent to 1 mod 4, right. Okay. So, what happens is A by 2 plus D by 2 square root of D sorry, this should be B by 2. This belongs to Z plus, sorry, this belongs to OK if and only if, yeah, with A and B odd, oops, if and only if D is congruent to 1 mod 4. Okay. So, what we have proven now is OK is equal to Z square root of D if D is congruent to 2 or 3 mod 4, and this is Z. If you check what we have proven, then you can write it like this: if D is congruent to 1 mod 4. Okay. All right. And now we can also compute the discriminant. So, what is dk? Right. So, let us assume first that so k is q square root of d, and as before d is a square free integer. So, let us take two cases. So, d is congruent to 2 or 3 mod 4 and d is congruent to 1 mod 4. Right. So, in this case, in the first case 1 and square root of d is integral basis, is an integral basis of OK, and in this case we already computed the discriminant. It is just delta squared of 1 and square root of d, which we computed was 4d. New thing happens here. So, here we proved that 1 plus 1 square root of d by 2 is an integral basis of OK, and so we have to compute. So, dk is 1 delta squared of 1 plus square root of d by 2, right, which interestingly is determinant of trace of 1 plus square root of d by 2, trace of 1 plus square root of d by 2, and then trace of square of this 1 plus square root of d square, which is so 1 plus d plus 2 square root of d by 4, right. Okay. So, if we compute this, this is determinant of 2, and what is this? This is 1, and the trace of this is also 1, and what is the trace of this? Well, the trace of this part goes away, and the trace of this is d plus 1 by 2, right, which is equal to d plus 1 minus 1, which is d. Okay, all right. So, so this is the calculation of the discriminant, right, and you see if d is congruent to 1 mod 4, we get dk is d, and if d is not congruent to 1 mod 4, we get dk is 4d. So, again yeah, dk is 0 mod 4. So, it is either 1 mod 4 or 0 mod 4. All right. So, let me also point out one more thing is that yeah, so what happens? So, if you take k to be q square root of d, again as before the same notation, d is square free integer. So, if d is bigger than 0, we get a real quadratic field, and in this case R1 is 2 and R2 is equal to 0, okay, and dk is either d or 4d. In any case, sine of dk is equal to minus 1 to the 0, which is 1, right. So, it is a positive thing, and now if dk, if d is less than 0, then R1 is 0 and R2 is actually just 1, because there is one pair of complex embeddings, and again dk is d or 4d depending on the congruence. I am not going to write it down, and you see that sine of dk is minus 1 to the 1, which is minus 1. So, it is a negative, right. So, this is the exercise that I gave you. Now, let me stop with a nice observation of Stickelberger, which is very curious, because there is no reason a priori to believe something like this. For any number field, k, the discriminant, it is an algebra, it is an integer, it is a rational integer, but it is always 0 or 1 mod 4, right. Whatever observation I made on this page, that dk is always 0 or 1 mod 4, is actually true more generally for any discriminant. Now, you would expect this for squares, and although dk is determinant of m squared, determinant of m is not necessarily an integer, right. So, you can't just say that dk is determinant of m square, and so it is always 0 or 1 mod 4, that is not correct, right. So, it is kind of curious that this still holds, and the proof is not that difficult. Let me write it down for you. So, what is dk? So, dk, recall, is determinant of m squared, which is writing this as summation pi belongs to the symmetric group on n symbols. So, pi, so Sn is symmetric group on 1 up to n, and pi is an element of that, and that is exactly how determinant is defined, sine product I going from 1 to n sigma I alpha of pi I, right. That is how the determinant of m is, and then you take square, right. So, it is a square of something, but that something is not necessarily an integer. Nevertheless, you can write this dk as a minus 2b square, which is a squared plus 4b squared minus ab. But what are these a's and b's? Well, a is simply taking all the a is just this thing without the sign. So, you take summation pi in Sn, you forget about the sign, and you just write this right. So, it's just it's like determinant, but I have forgotten about the signs, and then B is you just take everything with odd things, right. So, product pi in Sn, pi odd, this is product, and then you again forget about the sign, but these are only half of the permutations, and so it is clear that determinant of M is A minus 2B, and that is why dk is A minus 2B whole square, and so I have written it like this, right. And now here is an exercise, it is a easy exercise by what I have said. A is in Z, right. So, it just means that A is invariant under all. So, see that A is invariant under all permutation, all embeddings of K into C, because of the way it is defined, and so it is a rational number, but it is also an algebraic integer because it is a linear combination of product of algebraic integers. So, that is why A is in Z. So, that gives you this exercise, this thing. Now, A is in Z and dk is in Z. So, 4 B squared minus AB, this is also in Z, and I can forget about this. So, right. So, this is a priori a rational number, right. So, for B squared minus AB, you cannot use the Galois invariant argument. The argument that you have to use is that B square minus AB is dk minus A squared divided by 4, right. So, it is a rational number, but it is also an algebraic integer. So, it is in Z. So, I have practically solved the exercise for you, and so you get that d squared is A squared mod 4, but now you have written it as a square of an integer modulo 4. So, dk is not square of an integer, but modulo 4 it is like square of an integer. So, that is why it is 0 or 1 mod 4. Okay. So, these are some of the properties of discriminant that we looked at today. We saw how to use properties of discriminant to find rings of integers of quadratic number fields, but this is where we are going to stop for now about discriminants. In the next lecture, we will study how factorization works in rings of integers. Okay. So, factorization of elements fails, and then factorizations of ideal holds, and that is what we are going to study next time.